sure you just watch it later. Okay. Okay, so it's been a while since we talked about work. So the formula for work is force times distance. And force is pounds often, and then distance is feet, and so then it's a foot-pound. Or sometimes if you're in the metric system, force is in newtons, and distance is meters, and then it's a newton-meter. Okay, so that's how you find work. So this problem has two aspects to it. First of all, there's the load of coal that you have to lift to the top of the mine shaft. That load of coal weighs 200 pounds, and you're going to lift it 500 feet. So that part of the problem is pretty easy. To figure out the work, you just take the 200 pounds times the 500 feet, and that gives you 100,000 foot-pounds. So you just move a 500 pound or a 200 pound weight 500 feet, that's 100,000 foot-pounds. Okay, but the other part of the problem is you also have to lift the cable out of there, because the cable is pretty weighty. So we have to figure out how much work is done to lift the cable. And that's trickier, because at first there's 500 feet of cable, but then a second later there's 499 feet of cable, and then there's 499, 498, et cetera, et cetera, et cetera. So the amount of cable that you're lifting is constantly changing. So because of that, we need a variable for the amount of cable that we're lifting. So x is going to represent how many feet of cable that we're currently lifting. So at the start of the problem, x is 500. So at the start of the problem, when you have 500 feet of cable, how much does that 500 feet of cable weigh? 1,000 pounds, right? Because the cable weighs 2 pounds per foot. So if you have 500 feet of cable, it's going to weigh 500 times 2 pounds, 1,000 pounds. Okay, so if you have x feet of cable, it's going to weigh 2x pounds. So x is representing the length of the cable that's currently out, which keeps changing as you lift. And then 2x represents how much that cable weighs. Okay, now how far do you move a particular length of cable? A very tiny amount, right? Because the second you move it, it's shorter. So this number of pounds is only moved an infinitely small bit. So we're going to multiply that by dx. Okay, so the 2x represents the pounds, and the dx represents the feet that we move those pounds in. And then this is foot-pound. So what we have is 1,000 times a very little bit, and then 999 times a very little bit, and then 998 times a very little bit. And we're going to add all those up. So we're going to take the integral of that. And x changes from 0 to 500. So this represents how much work we do to lift the cable out. We already had figured out how much work we do to lift the coal out of the hole. Now this is the amount of work to lift the cable out. So of course the antiderivative of that is x squared. And then you plug 500 in and 0 in. So you get 250,000 foot-pounds. We already had the 100,000 foot-pounds for the coal. So the final answer to the problem is 350,000 foot-pounds. Okay, the next problem is about a cylindrical tank. with radius 2 feet. And height 8 feet is full of water. And the question is, how much work is done to lift the water? I guess we're not lifting, we're probably pumping the water, to pump the water out of the tank. Okay, so we have this cylinder. And the radius is 2 feet. The height is 8 feet. I guess now that I think about it, there isn't really anything that specifies in the problem that the cylinder is got the circles on the top and the bottom. There could be a cylinder tank that has circles in the front and back. So I'll just add that this cylinder has the circles on the top and the bottom. Okay, so there that is. That's full of water. Okay, now here's a bad way to pump water out of a tank. If you have a hose that goes all the way to the bottom of the tank, then what happens is you have to take the water from the bottom of the tank and pump it all the way out. And then the water keeps falling. And if you do that, if the hose is at the bottom of the tank, all of the water has to get pumped a distance of 8 feet. And that's kind of silly because some of the water up here isn't all the way down at 8 feet. So you shouldn't put the hose in the bottom of the tank and pump it all out 8 feet. So knowing that now, the next time you have a drink with a straw, you can save yourself a lot of energy by not having the straw in the bottom of the drink. You want to have the straw at the top of the drink because then it's easier. I know you guys get tired at the end of the day. I'm just trying to save you some extra energy for thinking about calculus, right? So yeah, okay, so yeah, you need one of those, you need a straw that's compressible, right? So that it can be really short and then you lengthen it as you get to the bottom, right? Okay, good. Yes, good. You're thinking right. You're thinking awesome, George. You're on top. He's really trying to save extra energy for calculus, you can tell. All right, so anyway, that's what we're not going to put the hose in the bottom. We're going to have a contraption where the hose floats on the top, and then as it goes down, it just kind of goes down with it, so that we don't have to pump all the water all the way out. We can just pump the top water just a little bit and the middle water just half the way. Okay, so what we want to do is think about a representative bit of water. So I'm going to go down about halfway. There's no reason I should go half. So here's a bit of water that we're going to pump out. And we're going to figure out how much work we're going to do to pump that water out first. And then we're going to worry about the rest of the tank later. So for right now, we're just figuring out how much work are we going to do to pump this little bit of water out. So that water, we're going to say, is down y feet. And we need to find the volume of that water. It's a cylinder in shape. So it's pi times 2 squared times dy. So pi 2 squared dy, that represents the volume of this cylinder, this tiny heighted cylinder. Okay, so then that's the number of cubic feet of water there are in that cylinder. Now, water weighs 62.4 pounds per cubic feet. So if we take this cubic feet and multiply by 62.4, now all of this is the number of pounds of water in that little bit of water. Now we need to take the number of pounds, that's the force, and multiply it by the distance we're going to move it to get the work. So we're using this formula, work equals force times distance. So all of this is the pounds. Is everybody okay with that? Now we just need to multiply it by the distance that it gets moved. Well, you can see in the picture, the distance it gets moved is y. So we multiply that by y. And now this represents the number of foot-pounds that it takes to move that bit of water from where it is to the top of the tank. Now, of course, we're not going to just move that water. We're also going to move this cylinder of water, and this one, and this one, and this one, and this one. So we have to add up all of those little bits of work. So we're going to integrate that from 0 to 8. Okay, so then 4 times 62.4 is 249.6, I believe. So I'm going to pull that out. Just because that's a constant. So I just took all of this, which was a number, and pulled it in front of the integral. Now I'm going to take the antiderivative. So that's 1/2 y squared from 0 to 8 times 249.6. So then you plug the 8 in, so that's 1/2 times 8 squared minus 1/2 times 0 squared. All of that multiplied by, I forgot my pi up here, sorry. 249.6 pi. So that's going to end up being 32. So 249.6 pi times 32. So that's 25,092.529. What would the label be there? The force is in pounds, but then we multiplied it times the distance, which is in feet. So this is in foot-pounds. So final answer for that problem is 25,092.529 foot-pounds. Okay, so that was part A. Part A was how much water is done to pump the water out of the tank. Now for part B, we're going to change it up a little bit. We're going to say how much work is done to pump half of the water out of the tank. And the knee-jerk answer here is it's going to take half as much work, right? If you're pumping half as much water, it should be half as much work. Why is that not correct? Because the water at the bottom of the tank is a lot harder to pump out of the tank as opposed to the water at the top. Because you have to move the water at the top less distance. That's why we want this floaty hose pump sort of thing that stays on top of the water. It saves us a lot of energy. Okay, so all we're going to do, though, to do the top half, it's the exact same problem. It's just 0 to 4 instead of 0 to 8, right? Because we're doing the top half. So it's not hard once you understand part A. So same exact integral, just from 0 to 4. Yeah, I'm calling y the depth. So when y is 0, we're at a depth of 0. Okay, so then it turns out that this is 25,092. 6,273.132 foot-pounds. I'm just checking that third decimal places. Yeah, that's right. So I've always found this kind of interesting. This is a fourth of this. If you take 4 times 6,000, it's 24,000. It turns out that this is exactly a fourth of this. So to do the top half of the water, it takes a fourth as much work. Interesting. Okay, for part C, we're going to change it up, and we're going to say that the tank is buried. Find the amount of work done if the tank is buried 5 feet underground and we are pumping to ground level. So same scenario, same tank, but now it's buried a little bit underground. So here is ground level, and then the tank is below ground level. And it's 5 feet below ground level. So I still have my sliver of water. And the volume of that water is still pi times 2 squared times dy. So there's the number of cubic feet for my water. Then I multiply that by 62.4, because that's how much water weighs per cubic foot. So now I've got the number of pounds of water. So that's my force. Now I just need to multiply it by a distance. So I have a choice to make here. I can make y represent the distance from the top of the tank down. And if I do that, then I'm going to move the water y plus 5. And then the water exists from 0 to 8. If I make that choice, where y represents from the top of the tank down. Okay, so that's method one. But you could also make a different decision and have y represent the distance from the ground down, right? So then you'd have 62.4 times pi. The volume doesn't change. How much the water weighs doesn't change. Now we're moving the water a distance of y. If we choose for y to be the distance from the ground down. Okay, but then the water starts at 5 and goes to 13 in that case. If y represents the distance from the ground down, we just want water to be from 5 to 13. So both of these ways will give the same answer. It's just depending on what you want your y to represent. The top method is if y represents the distance from the top of the tank down, and the second method is when y represents the distance from the ground down. There's ground down, there's top of the tank down. You'll get the same answer either way. Okay. So now for part D. The tank is conical instead of cylindrical. So instead of having a cylinder tank, now we have a tank that's in the shape of a cone. Now again, I'm not really specifying which way the cone is oriented, but I think this time we know which way it has to be oriented. What's the only way where it could hold water? Yeah, the circle has to be at the top with the point at the bottom, right? If it's going to hold water. Okay, so here's our tank. And we're just going to pump the water to the top of the tank. We're not going to pretend that it's buried or anything on this one. Okay, so now we want to have y represent the distance from the top of the tank down, and we've got a bit of water that's at that depth, right? So think carefully before you answer this question. What is the shape of the water at that depth? It's still a cylinder. Now it's not a perfect cylinder because the top circle is a little bit larger than the bottom circle. But that's going to be just fine when we go infinitely thin, right? Okay, so a lot of times people think, hey, in A, B, and C, the tank was a cylinder, and so the shape of the water was a cylinder. So that means on this one, the shape of the water is going to be a cone. But you see why the shape of the water at that depth is still cylindrical? What is harder, though, is the fact that this radius here is not 2. And what makes it even harder is the fact that that radius for that bit of water is different than that radius for that bit of water. So the radius is changing, is what I'm trying to get across here. On the last problem, no matter how deep you were, the radius was always 2. But here, as you go down, the radius is getting smaller. Okay, so we need a variable for our radius, because it changes. Okay, so what's the volume of that bit of water. Just that bit there. Pi r squared dy, right? Okay, so the volume of the water is pi r squared dy. That's the number of cubic feet of water. So then I need to multiply that by 62.4 to get how many pounds it weighs. So now I have the number of pounds that the water weighs, which is also the same as the number of pounds of force that I'm going to require to move it. Okay, so this is pounds now. And then I need to multiply by how far I move it. So how far do I move it? A distance of y. So I multiply that by y. So now I have foot-pounds to move just that little bit of water. And then I add them all up. I didn't mention, but this is still a radius of 2 up here. And this is still a height of 8 feet here. So I want to go from 0 to 8 on my y, right? So now everything's really good, except I have to somehow figure out what this r is. Because I can't have an r mixed with a y in the same problem. It's got to all be y's. All right, so to accomplish a formula for r, I'm going to look back here at what r is. So let me get rid of this extra water here. There's a triangle in here inside the cone that's r this way and height that much. And then there's another triangle in here that's here that's 2 this way and 8 this way. So I'm going to draw those two triangles. So there's the smaller triangle that has a radius of r. And there's the larger triangle that has a radius of 2 and a height of 8. These triangles are similar. So that means I can set up a proportion to figure out r. But before I can do that, I need to know what this is. So let's go back to our picture. This is 8. This is y. So this is 8 minus y. In other words, if we're down at a depth of 6, that's going to be 2. Or if we're down at a depth of 7, that's going to be 1. So it's 8 minus the depth to get the height of the triangle. So now over here, this is 8 minus y. So now we can set up our proportion. R over 2 equals 8 minus y over 8. And then you cross multiply from there to get the formula for r. So 8r equals 16 minus 2y. And divide both sides by 8. The 8 distributes. 16 minus 8 is the 2. 2 minus 8 is the 1/4. Not minus. I said minus, I mean divide. 16 divided by 8 is 2. 2 divided by 8 is 1/4. So there's my formula for r that I can plug in over here. So I've got the integral from 0 to 8, 62.4 pi times 2 minus 1/4 y squared y dy. If we were going to do this by hand, we'd have to square this out. and then distribute the y. I would take the 62.4 pi out front. But it's also okay to, I mean, you want to practice your algebra some of the time, but it's also okay to do math 9 some of the time. Okay, everybody doing okay so far? All right, so this was 7.5b, but I also want to remind you what happened in 7.5a because it was a long time ago. So in 7.5a, the problems were about pressure. So what was happening in 7.5a is there was water sitting in a tank, but we weren't pumping it out. It was just sitting there. Or there was a dam, and there was water behind the dam, and it was just pressing against the dam. So the question in 7.5a was, how much pressure is there on the front of the tank or on the dam, etc.? Okay, so I want to remind you how to do that. What you have to figure out is, so maybe here's the front of the tank, and there's water behind it, right, pressing on this. So what we did was we divvied this front plate up into a bunch of rectangles. And we found the amount of pressure on the rectangle. And then we added up all the pressures on all of the rectangles. And we had a variable that represented the depth, just like we did in these problems. Because as you go down deeper in the water, there's more water pressure. If you dive down 10 feet, your ears start to hurt because the water's pressing on you. So as you go down deeper, there's more water pressure. Okay, so water weighs 62.4 pounds per cubic foot. So if you multiply that by the depth, which is in feet, you get the number of pounds per square foot. So all of this here, 62.4y, that represents the number of pounds per square foot that is felt at that depth. Then you just have to multiply that by the area of the rectangle, which would be in square feet. And then after that, your final answer is in pounds. And that's the number of pounds of pressure that's being felt. So that's a different kind of problem, where the water was just sitting there, and we wanted to know how much pressure was felt. So the final answer was in pounds. Whereas today, we were doing work problems. So we actually had to take the water and lift it out of there, and then the final answer was foot-pounds, how much it weighed or how much force it took to move it, times how far you're moving it. Okay, so the reason I bring that up is there are a couple of questions that are a review from 7.5a on the homework. I put those at the end of the assignment, but they're the lower numbers. You know how I do that? Sometimes I assign 20 and then 22 and then number 5, and everybody's confused because they're wondering why I'm assigning 5. It's because I want you to do those last so that you do the review problems after you do the new kinds of things. Okay, everybody good? Thanks for listening.